In this video, I'll be going over the question 40 from paper 13 from the summer administration of the ACE Physics exam 2013, paper 13. A radioactive nucleus is formed by beta decay. The nucleus then decays by alpha emission. Which graph of nucleon number N plotted against proton number Z shows the beta decay followed by the alpha emission? So beta decay is when we eject a high-speed electron from the nucleus. Again, we need the weak nuclear force to be able to explain, like, how could a electron come from the nucleus? All right. So what happens is a neutron transmutes to a proton, it becomes positive, and it kicks out sort of the negative charge. And so what happens to the proton number Z after this beta decay is it goes up by 1. And so does anybody see evidence of that? It says, which graph of nucleon number N plotted against proton number Z shows the beta decay, followed by alpha emission? And so we're basically looking for, the first thing it needs to do is go up by 1 on here. So it's like going from here to here. Here it looks like it's going down 1. Here it looks like it's going down 1. Here it looks like it's going down 1. But it would go up 1, right? Because we'd be at 91 and we'd go to 92. And then the alpha decay, remember an alpha particle is a helium nucleus. And so it would drop from we went up from 91 to 92, but then we go down to 90. And we'd also drop 4 nucleon numbers. So I think they all show, like this one showing dropping 4 nucleon numbers. This one only drops 2. This one only drops 2. So like these two are incorrect because they do not decrease by the correct amount of nucleon numbers. This one is incorrect because it's showing 93 protons becoming 92. But we don't go down in proton number for at least beta minus decay. Now they don't really tell us if it's beta minus or beta plus decay. There is a type of decay, beta plus, where you emit a positron. Okay. And that's when a proton becomes a neutron. So you can have this happening in beta plus decay. And then it still would go down by 2 after that. And so, yeah, I guess if it's beta plus decay, it could be A. But I would say if it doesn't tell you otherwise, we can assume it's more typical that a beta minus particle is decayed. This is the reaction that tends to occur. A proton decaying, if that happened, that'd be big news, okay? As far as we know, protons are very stable and they do not decay. Now they can, I should say a lone proton, can have like nuclei that are being formed where if you have an overabundance of, say, protons, they can become neutrons while they're still bound due to this weak interaction because it acts over, both the quarks and the leptons, sort of inside the nucleus. But there are experiments that are sort of, running that are looking for proton decay. If we calculate the lifetime of like how long should it take a proton to decay, it's longer than the current age of the universe. And so we don't expect to see protons decaying anytime soon, lone protons. So I think B is the best answer for this. And that's just keeping track of that idea that nucleon number and proton number is the same. When we go to look up our answers, if it's not B, but A, we would have got the one wrong and everybody will lose, a mark on the quiz. This one reads, the decay of a nucleus of neptunium is accompanied by the emission of a beta particle and gamma radiation. What effect, if any, does this decay have on the proton number and on the nucleon number of the nucleus? When we emit a beta particle, we increase the proton number. Remember, we just said, if it's a beta minus particle, then a neutron is becoming a proton, so it's going to increase. So either choice A or D. The nucleon number is going to be unchanged, though, because it's still in the nucleus, right? So it's just that a neutron has to become a proton. So the proton number goes up, but the actual number of nucleons doesn't change at all. And so D has to be the correct answer for this one. Question 38 here is still dealing with radioactivity. And so, like I said, it's usually like, 2 or 3, sometimes 4 questions, but always at the end of paper 1, you get some radioactivity questions. Scientists investigating the count rate from a radioactive source observed that the count rate fluctuates. What do these fluctuations imply about the nature of radioactive decay? That it involves atomic nuclei, it is predictable, it is random, or it is spontaneous. It's certainly not predictable if it fluctuates. It involves atomic nuclei, I think is correct, but the fluctuations don't sort of, this evidence doesn't imply that, right? And so it's either like it's random or spontaneous. So remember we said, what does it mean to be spontaneous? There are no external factors that can influence it. So they're just looking at it and they're saying, hey, the count rate is fluctuating. Does that mean that it's random or does that mean that it's spontaneous? Well, spontaneous would be like if the scientists actually did something and then they still noticed it doesn't affect it. Like the scientists tried to heat it up and it still didn't change. It tried to cool it down. It tried to increase the pressure. So I really think that C is the best answer. It's just saying, hey, it's random. It just randomly sort of decays when it wants to. But over a long period of time, you'd probably be able to average that, oh, it tends to decay at this rate. So any individual decay reaction is random, but we can still sort of bring some form to it by averaging and get like the half-life of certain radioactive substances. Let's see if we had a question 37. That was radioactivity. Nope, getting the circuits there. Remember that stuff. So hopefully somebody gets some circuit questions tomorrow so we can jog our memory about that. All right, so to give ourselves feedback here, let's say C, D, and then D, D. There we go, CDB. We keep our good streak going, okay? And again, tomorrow, be very careful because if we miss one, it's going to affect everybody. And if you could be the person to catch the mistake, now what if you think it's a mistake, but it's not, and we change our answer that was right, and then we make it wrong? That would not be cool. So, I mean, but that can happen in a test. You second guess yourself. You're like, oh, let me check my work. And then you sort of check it and you're like, oh, wait, I get a different answer. Should I change it? Should I go with my first instinct? I mean, I would say if you can really prove to yourself that like you made a mistake and you clearly see, oh, I was wrong, go with the second answer. But oftentimes our intuition is correct. Like the first sort of thought that we have on it is right. Although, we saw a counter example just a moment ago where upon first inspection, I really thought that the increasing activity of the alpha source would be the answer to that other one, but it was the thickness of the foil. But I mean, when you think about it just a moment longer, you can get there to the right answer. All right, I heard somebody out there say, what about a paper 2? We've been doing all these paper 1 questions. Are we going to do a paper 2 here? It's 3 o'clock, that's going to end in 30 minutes. I hear you. Okay, we'll do a paper 2. Let's stick with this 2013 though. This is a good year. I like paper 22 from the Winter administration. And what's the radioactivity question on this one? All right, it says an electric field is set up between 2 parallel metal plates in a vacuum. The deflection of alpha particles as they pass between the plates is shown. So we got alpha particle that goes in here. They're showing us the direction of the field. Remember that alpha particle is just 2 protons, right? It's a helium nucleus. And so it's going to move in the same direction as a proton would move, right? In the direction of the electric field. And so it gets deflected this way because there's, that's the way that a proton would move. And it's two protons. All right. And then it says the electric field strength between the plates is reduced. And so they show less field lines. Remember, one way to represent the strength of the field is by the number of lines that you draw. And so they've drawn only 4 lines as opposed to however many this is. The alpha particles are replaced by beta particles. The deflection of the beta particles is shown. Okay, and they're showing sort of that there. All right. State one similarity of the electric fields shown in figures 7.1 and 7.2. One similarity of the electric field. Well, they point in the same direction. That's what I would say, right? They're both pointing down. It then says the electric field strength in 7.2 is less than 7.1. State two methods of reducing this electric field strength. These are kind of softball questions in my opinion. How do we reduce the electric field strength? Well, I mean, if you're mindful of the physics, right? Electric field is the force per charge. It is the voltage per distance. You can't really affect the force on the charge or the charge. Like we can't change the charge of our beta particle. We can't really affect the force on it. The things that we're in control of in our lab is what's the voltage between these plates? What's the distance between them? Like these are the things that we can manipulate in the lab to change the electric field. We know it's equal to this, so we can calculate like, hey, yeah, what was the force on this thing? How much charge was there? So how would you reduce the field strength? Well, you could either decrease the numerator or you could increase the denominator, right? Both of those will have the effect of reducing it. So kind of put that into words. You could say decrease the voltage or the potential difference between the plates, or you could increase the distance between the plates. Between the plates. Both of those would reduce the electric field strength. And the equations that I'm erasing right now are the way to sort of bring form to your thoughts, to say, well, here's the equation that governs this. What manipulations have to occur to these variables in order to, reduce it? Yeah, these are, very straightforward questions. They're going to give us a tough one here, maybe. It says, by reference to the properties of alpha particles and beta particles, suggest 3 reasons for the differences in the deflections shown in the figures there. So this is kind of a tricky question because it's 3 marks and it's like, if you don't have any idea, it's going to be obvious to the person grading it that you don't know. Okay, you can't BS your way through it probably. I mean, maybe, but usually it's obvious when students do that and you can hardly ever get to the correct answer by just sort of putting some academic language down and thinking like, oh, this sounds scientific, but is it right? Is it actually sort of answering it? So always follow directions. Always answer the questions asked. Make sure if they say, hey, by reference to these properties, make sure you're referencing the properties. And we'll go over sort of, the more of those properties tomorrow. Alpha particles are more massive than beta particles, right? They're made up of 4 nucleons. This one is electron. It's not even a hadron at all, okay? So a beta particle is an electron. So why would there be the differences? And so what were the differences? The alpha particle kind of went like that through the field, and the beta particles went like there's 3 of them, first of all, and they had sort of different angles of deflection, and they went up. They also didn't make it all the way through the field, okay? Well, why? Because the beta particle is so much lighter, so much less massive than the alpha particle that it gets pushed around. Don't forget Newton's second law. When these particles, these charged particles, this is negatively charged, this has a charge of +2 elementary charges, this has a charge of, -1 elementary charge. As these charges go into an electric field, they feel a force, right? The force per charge. So they get accelerated. When things feel a force, they get accelerated, but according to how much mass there is, right? So more massive things that are more inert, like alpha particles, don't accelerate as much, which is why you see a very little deflection, because it's got more inertia, more mass. But the beta particles, they went up really quickly, right? They don't make it even all the way through the field if you study those sort of figures carefully. All right, so like this one makes it through. It's deflected not at the same sort of an angle as these ones, which are very sharply deflected so that none of them make it out of the field. Okay. Let me take a moment to jump on a little history of science here. It was this kind of observation that led to the hypothesis of the neutrino. We said, why are these beta particles of all different energies? Really, like the only way to explain why, like this one makes it here, but some other beta particle made it to here. This one must have had more energy when it went in. It had higher velocity. How could these particles that are coming from the nucleus have different energies when energy is neither created nor destroyed? Like these are the same particles. It led scientists to think maybe there's some other particle that's really tough to detect that's also in there, like taking away energy. And so it was in like the 1930s that Wolfgang Pauli, based on sort of looking at experimental evidence like this, and he was really a theorist, came up with maybe there's a particle called a neutrino that was discovered about 20 years later. So it took about 2 decades, but we eventually discovered neutrinos. And so here we can see that, like, well, you know, an obvious difference is this one goes down. Why? Because it's positively charged, as we said. So by referencing what the alpha particle is, we say it moves down in the field because it's going in the direction of the field. Because the beta particle is negatively charged, it moves against the direction of an electric field, right? Because it's an electron. Remember, electrons move opposite from protons. They're also less massive, and so they don't make it as far into the field. They also have a range of energies. Okay, there's a range of energy here of these beta particles. And so any of those things you kind of put into your own words. If you want at least 3 of them. And so once again, think about what are the differences in the deflections? And then you have to say, well, why are there those differences, right? What are the reasons for it? And you have to reference what these particles are. And so the properties of the particles, once again, are that the alpha particles, alpha, beta, alpha particles more massive. An alpha particle has a mass of about 6.68 by 10 to the negative 27 kilograms. A beta particle has a mass of 9.11 by 10 to the negative 31 kilograms. That's a negative 24. That's a good stuff. What's a couple of orders? So it's about 10,000 times, you know, more massive, which means it's going to make it further through the field. It's not going to be deflected as much as per Newton's second law of motion, right? So more massive things don't get accelerated as much. The force, you know, sort of is the same. Oh, wait a minute. What else are we're forgetting that we decrease the strength of the field? Yeah, you're good. We decrease the strength of the field here too, so there's less force acting on it. If we would have had this, okay, and so what if we would have sent the beta particles into this field? Like, what if we didn't reduce it? What would that look like? It's just a stronger field, so it's a stronger force. And so basically, instead of even making it this, like they had to decrease the field strength to even get these results, because if not, they would have been something like that. Like it would have immediately crashed into like this. This field is strong enough to deflect a alpha particle that's 10,000 times more massive than a beta particle. So if you were to just like fling a beta particle into that, it's just going to immediately just crash into the top plate. You won't even get a sort of a path. And so it's like to even see these beta particles, you know, showing up here, they have to decrease the strength of the field. That's another thing I forget. We didn't keep the field strength constant, but I don't think it affects any of our answers. So the alpha particle is more massive than the beta particle. If you wanted to quantify that, those are the sort of values there. So that's the property. That means the difference is this one makes it further through the field. Okay, these ones are deflected more sharply. That's the difference that you see in the deflection. This one is positively charged. It has a charge of plus 2e. This one has a charge of minus 1e. So because there is a stronger I'm sorry, because it is positively charged, then it's going to move in a different direction, right? So one property of the alpha particle is that it's positively charged, and means that one reason that it's different, it's going to move down or in the direction of the electric field. This will move in the opposite direction of the electric field, right? Because of its property that it's negatively charged. And I suppose you could say that the beta particles, can exist in a range of energies, which is why you can see sort of different, different kinetic energies, which is why they have sort of different paths in the electric field. So that's another property. The beta particles can have a range of energies. So too could the alpha particles, I suppose. The amount of charge is also different. So it's like this one is positive, this one's negative, but there's twice as many charges in this one as that one. Those are all the key differences there. And now we finally have a source of alpha particles is uranium-238. So it's radioactive. It will sort of emit alpha particles. The nuclear reaction for the emission of alpha particles is represented by this equation. And we want to state the values of all of these variables, W, X, Y, Z. So we're using the same idea of nucleon and mass number being nucleon number and proton number being conserved. If we know this is an alpha particle, then we know that this Y is 4, and this is, remember that an alpha particle is a 4 to helium, 4 nucleons, 2 protons. And then that's all we need to sort of fill in the rest of this, right? So if this is 92, and this Z over here is 2, that means that X here must be 90. And if this is 4 and this is 238, then we need to add 234 to 4 to get 238. So it's what's that? Thorium. So 2 here is an element of thorium. So from paper to paper, you can kind of see how, sometimes it's a very involved question. Lots of, questions to answer about radioactivity. And other times it's like, oh, they only gave me a, like a 6 mark, sort of question, where this one might be, 11 marks or something like that, or 9 marks. You never really know year to year. A source of beta particles is phosphorus 32. The nuclear reaction for the emission of beta particles is represented here. State the values of all this. Once again, we're going to assume this is a beta minus sort of decay, because that's sort of more typical. And it could be that in 2013 they had the syllabus changed, and that's why they're like it was just beta minus decay, and they didn't sort of add in beta plus decay until sort of later. But I don't think that. All right, so we kind of have to start with this, like we should know something about the beta particle, and then we just use our math to sort of use A and B over here. So if this is a beta minus particle, it's an electron, which means its proton number is 0, or its nucleon number is 0. But I think what we actually need to do is say it's not a proton, but we don't, is it a 0, 0? Or do we make it a 0? And because it's negative, we have to make it negative 1. Because remember, we're thinking about what happened to one of these nucleons in phosphorus. One of these neutrons up here became a proton. So it's like the 32 stays the same. Like A still has to be 32. But this 15 went up to 16. Okay, so B has to be 16. We need to add what to that to make it 15. And so we should say that B is negative 1. And then C has got to be 0. So a beta minus particle, an electron, okay, beta minus particle has this nuclide symbol. The other day we saw that a neutron is always going to look like that. I'm sorry, that, right? It's not a proton, but it is a nucleon. A proton, that was like that, hydrogen. And this would be an electron, okay, or a beta minus particle. Even though it's not a proton, what's its proton number? You gotta make it negative 1. Okay, so I'm pretty sure when we go to look up the answers here, which this will be the last thing we kind of do, we'll start packing it up. I think we're gonna get these answers here. You guys write down W, X, Y, Z. 234.94.2, right? All right, going through here. The direction of the fields is the same, or the fields are uniform, or constant electric field strength, or E equals V over D with the symbols explained. So those are saying like, what are some differences? And I think, or the similarity, right? And I said, well, they point in the same direction, right? This is kind of the obvious one, but there's other correct things you could have said about that. Reduce the voltage, increase the separation. And it says of the plate, of the plate. And so see how they've underlined that? I don't know if, it's careful in our language to sort of state that. But remember, that's the thing that we can manipulate. We can change like how close these plates are together, how much voltage is sort of put on them. So alpha has the opposite charge to be, as it's deflecting the opposite direction. Beta has a range of velocities or energies. So remember, we did say that there's this range of velocities. Alpha all have the same velocity or energy. There's a constant deflection. The alpha particles are more massive as the deflection is far less for a greater field strength. So yeah, I feel pretty good about all three of those marks. 234.94.2, 32.16.0, and indeed -1 for D there. All right. I hope you all have enjoyed going through these physics questions just as much as I have. This is Dr. Schleif signing off.